And now it's time for sulfur-containing compounds. We've talked alcohols, we've talked ethers, we've talked epoxides. It's time for sulfur-containing compounds. Actually, we talked alcohols, we talked sulfonate esters, we talked ethers, we talked epoxides. Now it's time for sulfur-containing compounds other than sulfonate esters. Thiols are the sulfur analogs of alcohols. What does that mean? Here's an alcohol. If you change that O into an S, that's a thiol. Thiols are more acidic than alcohols. Why so? Because the S is bigger, it's more acidic. Oxygen and sulfur are upstairs, downstairs neighbors on the periodic table. It's about size when you compare things up and down the periodic table. Yeah. The sulfhydryl group, that's what some other disciplines call it. The sulfhydryl group is present in natural systems. Sulfur is a common element in physiological systems. Yeah. We've seen a good many sulfur reactions already, in that we've seen sulfurs as nucleophiles with alkyl halides. If we see that this is an alkyl halide, we say, that's a secondary alkyl halide. So I'm going to look at the flow chart. And the flow chart says secondary alkyl halides, am I adding anions? Yes. That sulfur is an anion. Is that anion a strong base? No. I'm going backwards. Sulfur is bigger, therefore it's more acidic. What that also translates to mean is O- versus S-. O- we said is the weakest thing that we will call a strong base. So if O- is the weakest thing that we will call a strong base, we know that S- is even weaker than that because SH is a stronger acid than OH. So S-, weak base. We got anions, yes. Strong base, no. Therefore, SN2. Sulfur is very good at being an SN2 nucleophile. It's also good at being SN2'd upon. So this is sulfur acting as the nucleophile to do an SN2, but it's also good at being SN2'd upon. We'll see that. SN2. Inversion. My S is pointed backwards. Yeah. That's old news, right? Yeah, old news. Here's a sulfur with 2 carbon groups. That's called a sulfide, also called a thioether. It's an oxygen with carbon on ether side. That's an ether. There's a thioether. Exchange the oxygen for a sulfur. You put in the name thio instead of just regular ether. All right. We're adding, what is this? Why do we have 2 pluses? I don't know. Forget that plus. We're adding a methyl alkyl halide. Alkyl halides follow the flow chart, and the flow chart says methyl SN2. Look, it already said it. Sulfur is good at doing SN2s because it's a good nucleophile. SN2. We get this stuff. This is a sulfonium. The is to tell me that the sulfur is positive. It's a sulfonium ion. This sulfonium ion can be SN2'd upon. What the heck are you saying, crazy lady? Sulfonium ions can be SN2'd upon. So when I add another nucleophile of some sort, I can attack my methyl group and let go of my sulfur. Sulfur is a decent leaving group when it's got a positive charge, because it can leave as a neutral sulfur compound. So the first reaction was sulfur acting as the nucleophile. The next reaction was sulfur acting as the leaving group. This sulfonium, don't know what just happened. This sulfonium is a good acceptor of electrons if you attack one of the carbon groups connected. So this sulfonium was easy to decide which side to connect to attack because they're all 3 methyl groups. since this is an SN2 reaction, if these three groups were different, I would need to attack the least crowded substrate. So if I had something like a sulfur with these groups on there, I would need to attack, the nucleophile needs to attack the least crowded one to let go, that sulfur's have positive, my bad, to let go of the sulfur, and the nucleophile escapes with the least crowded thing connected to it, while the sulfur keeps the bulky stuff connected to it. Yeah? You follow? Sulfur is good at doing SN2, and it's good at being SN2'd upon. So this top reaction is me showing sulfur doing SN2, bottom reaction showing sulfur being SN2'd upon, in this crazy way that I say that. I know. What kind of applications might this have in real life? Well, it's all about SAM. SAM stands for S-adenosylmethionine. Ever heard of methionine? This is methionine. It's an amino acid. It's one of the 20 essential amino acids. My laser's not showing up. This, PowerPoint. Ugh, makes me crazy. Okay, down here, finally. This is methionine. This guy. Oh, nope. The thing at the bottom, just above the plus H2O, that's methionine. This guy, methionine. Methionine has a sulfur in it. And that sulfur is good at doing SN2. We've seen ATP before. We saw it in a video previously about phosphorus being a good leaving group. We can SN2 that CH2 right there and let go of this OPP good leaving group, this pyrophosphate. They broke down differently, but we let go of our PPP pyrophosphate thing. Sulfur attacked SN2, like that. And you get this. This is SAM, S-adenosylmethionine. That's adenosine connected to a methionine. What's so great, what's so fancy about SAM? SAM has a methyl connected to that sulfur. That is a sulfonium, and that sulfonium can pass that methyl to other nucleophiles in our bodies. So that methyl gets passed on to lots of other nucleophiles, like this. Sorry, no, that's just making methionine. This says some acceptor, some nucleophile comes in, and it leaves with an extra methyl. Where did it get that extra methyl? It got it from SAM, S-adenosylmethionine. That methyl went away because it left with the acceptor. That's a biochemistry term to call it an acceptor. It's an organic chemistry term to call it a nucleophile. What kind of acceptors exist? One acceptor is norepinephrine. This norepinephrine has an NH3 and amine, and epinephrine has a methylamine on it. Where do you think that methyl came from? It came from SAM. That norepinephrine can attack this methyl. It's got to be an NH2 at that point. That norepinephrine attacks that methyl and lets go of the sulfur like that to give me epinephrine. It also converts phosphatidylethanolamine into phosphatidylcholine. Phosphatidylethanolamine is the NH2 version, NH3 plus version, where this is the part that I drew, but that lone pair on the NH2 attacks SAM and gets one methyl. It attacks another unit of SAM and gets another methyl. It attacks another unit of SAM and gets another methyl. It gets all three of those methyls from SAM, S-adenosylmethionine. Phosphatidylethanolamine is one of our phospholipids that's present in very small quantities in our lipid bilayer. Phosphatidylcholine is the most common phospholipid in our bodies. It is the biggest component of all of our phospholipid membranes. Yeah, it's kind of a big deal. And SAM gave it these three methyls, all of them. That's because sulfur is good at doing SN2 and good at being SN2'd upon. Yep. We had a lot to say about alcohols, a bit to say about ethers, a little bit more to say about epoxides. Not as much to say about sulfur-containing compounds, just that they're good at doing SN2 and being SN2'd upon. So we're going to go ahead and move along with amines in this same video. Amines are unreactive towards substitution and elimination. Why? We actually mentioned this in the very, very first video of this sequence. Nitrogen, if you're trying to do some sort of nucleophilic thing, like on that carbon right there, and let go of that nitrogen leaving group, you would have to kick out a nitrogen with a minus. Ooh. A nitrogen with a minus is a crazy strong base. And strong bases are terrible, horrible, no good, very bad leaving groups. Strong bases, awful leaving groups. With alcohols, we could react them with acid to make it a better leaving group. With amines, that's not possible. Amines cannot react with acid to make them a better leaving group. An amine with an H on it, if you add some sort of compound that's going to be a nucleophile to attack and let go of that amine, it's not going to work because it's going to just deprotonate that amine. So instead of doing substitution and elimination on amines, we just say amines are good bases themselves, and they're also pretty good nucleophiles themselves. They don't do SN2, SN1, E1, or E2 on themselves. They're good at attacking other things only. However, quaternary ammonium salts. Quaternary ammonium salts can do substitution or elimination. They only do one. I'll tell you what in a moment. Note, this is 3 methyl groups and another carbon group on this amine. That's what makes it a quaternary ammonium salt. It's officially a quaternary ammonium hydroxide because that matters. We'll talk about it. Quaternary ammonium hydroxides do not do substitution. They only do elimination. And if you had to guess, do you think they would do E1 or E2 based on the fact that there's hydroxide in solution? There are 5 times that you get a carbocation in the presence of a strong base. Never, 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 never. With hydroxide around, we're going to do E2. And E2 is the only reaction that quaternary ammonium hydroxides do. E2. So, if we heat this quaternary ammonium hydroxide, the amine thing is going to be my leaving group. My leaving group is always connected to the alpha carbon. So, leaving group connected to the alpha, that means beta is next door to that. E2 says, take a hydrogen from the beta, fold in electrons to make a new pi bond, and let your leaving group go. We get this new alkene and a nitrogen that left with a new lone pair, and we made water from where we used hydroxide to pluck that hydrogen. Quaternary ammonium hydroxides do E2 and E2 only. Yeah? E2 and E2 only. This example was unique in that it had only one type of beta hydrogen. What if you have multiple types of beta hydrogens? Quaternary ammonium salts give you anti-Zaitsev elimination. Anti-Zaitsev and anti-Zaitsev only. The first person to discover that they gave anti-Zaitsev and anti-Zaitsev only, his name was Hoffman. Don't remember if that has 2 F's, maybe it does. So instead of calling these products anti-Zaitsev products, we will more likely call them the Hoffman elimination products. Hoffman means anti-Zaitsev. Yeah? Okay. So what does Hoffman product stuff look like in an example? Oh, let's look. Connected to the nitrogen are all alpha carbons because nitrogen is our leaving group. Next door to alpha is beta. Zaitsev would say, pluck a hydrogen from the armpit over there because that carbon has the fewest hydrogens. Anti-Zaitsev would say, take one of these from the right beta because it's got more hydrogens. Hoffman is anti-Zaitsev. So our E2 mechanism looks like so. where we take the hydrogen, simultaneously dump in electrons to make a new pi bond, and kick out my nitrogen leaving group. There is my product. Yep, that's it. I kicked out my nitrogen. It left, but it didn't go very far. I just busted open my ring when I did this Hofmann elimination. This is a quaternary ammonium hydroxide. I think it's important that you know how to make quaternary ammonium hydroxides. So if you start with a regular plain amine, that amine can react with methyl iodide. This is excess. I had an old professor that wrote it that way. Excess methyl iodide in an SAN2 kind of way. SAN2, methyl iodide, methyl halogen, that's methyl alkyl halide. That's SAN2 and SN2 only. So we get this. Methyl got added. All right. Potassium carbonate, K2CO3. That's 2 K pluses and a CO3 2 minus. That's a base. That base can clean up that H to get you back to a neutral amine. And because you've got excess methyl iodide, you do another SN2. Like this. You get nitrogen. Oh, 1, 2, 3, 4. Nitrogen with a hydrogen and 2 methyl groups and a positive. Another potassium carbonate cleans up that hydrogen to give you a tertiary amine. That tertiary amine can react with one more equivalent of your methyl iodide to give you a quaternary ammonium salt. This crowded mess, here's my quaternary ammonium salt up here. It's a salt, that's the cation, but where is the anion? What is the anion? The anion in this salt is an I minus because you added methyl iodide again and again and again. That I minus is the anion to your quaternary ammonium salt. So this is a quaternary ammonium iodide. But I've tried to make a good point of saying, a good effort to say that quaternary ammonium hydroxides are what do these E2 reactions. So my quaternary ammonium iodide cannot undergo E2. You have to do this kind of thing, which is an anion exchange reaction. Anion exchange, meaning I need that I minus to turn into an OH minus because it's quaternary ammonium hydroxides that do E2. We are not going to draw the arrows of how that anion exchange works, but it's going to make some silver iodide precipitate is part of what it does. Yeah. We're making our I minus turn into an OH minus, anion exchange, that thing. Then when I heat this reaction, that's when my alpha beta hydrogen can be taken, E2, to give me that product, and an N with a bunch of methyls. But we don't care so much about what happens to the amine if they are two separate products. We care that we made the alkene product. Yep. That's quaternary ammonium hydroxides. Those things are nitrogens with 4 carbon groups connected and a positive charge and an anion hydroxide bundled with that cation. The cope elimination is a slight variation of these quaternary ammonium hydroxides. The cope elimination starts with a tertiary amine and turns that tertiary amine into a tertiary amine oxide. It can undergo intramolecular elimination instead of intermolecular. The ones we've been drawing are intermolecular. You get thin stereochemistry, but we're not going to talk a bunch of details about thin stereochemistry. It still gives you Hofmann. Uh-oh, that's got 1 F and 2 N's. I guess I spelled it wrong earlier. Whoops. How does that cope elimination work? Well, we start out with a tertiary amine, and we add hydrogen peroxide, which is an oxidizing agent. That undergoes an oxidation reaction. We're not going to draw curved arrows of how that oxidation happens, but we oxidize the nitrogen to become this. This is a tertiary amine oxide. Nitrogen, oxygen directly connected to each other with a positive and negative tertiary amine oxide. That can undergo elimination. We're going to draw some crazy arrows over here. It's reaching real far. It looks like it is. E2, intramolecular elimination like this, to give me those products. 3 carbons of my alkene and my NOH stuff as a side product. The excuse me. The cope-elimination is a special little variation on quaternary ammonium hydroxide doing E2 elimination. It's not a big reaction, but someone has told me before they saw it on their MCAT. Yeah, take with it what you wish. Provide a synthesis of butene from one butanamine. Well, obviously, if you have an amine, that amine, one butanamine, it's awful. One butanamine needs to be turned into butene. Well, how do I turn an amine into an alkene? Turn it into a quaternary ammonium hydroxide and then heat it. Okay, I can do that. This gets turned into a quaternary ammonium hydroxide with excess methyl iodide, methyl bromide, it doesn't really matter, and potassium carbonate. That turns it into this quaternary ammonium iodide, anion exchange with some silver stuff gives me a quaternary ammonium hydroxide. And then I cook that quaternary ammonium hydroxide, and magically I get one butene out of it. Ta-da! Yep. Okay. Ooh, this is a long problem. When piperidine undergoes the series of reactions indicated below, this series of reactions is often called a Hofmann degradation. When it undergoes a Hofmann degradation, 1,4-pentadiene is obtained as the product. Okay. When 4 different methyl-substituted piperidines undergo the same series of reaction, each forms a different diene. Which methyl-substituted piperidine yields which diene? Oh, brother. So let's start with drawing the methyl-substituted piperidines. There should be 4 of them. There's one. There's another. There's one. And my last one has a nitrogen methyl substituted thing. Yep. Because we said these steps are called Hofmann degradation, I'm just going to put HDs on all these arrows because I don't have enough room to write out all the stuff. But each of them needs to go through 2 Hofmann degradation steps like this. This is a HD, not a Harley Davidson. Okay, so we're going to make a Zaitsev product. So after the first Hofmann degradation, in this top example, we're going to make a new pi bond here. And we will have a nitrogen that's full with methyls, remember, because you got to have a totally positively charged nitrogen that you then bust open. In this bottom left, we're going to bust it open over there, like that. In the top right, our alphas and betas are no different, so I'll bust the left, it doesn't matter. Okay, and in the bottom right, our betas are also no different, so I'll bust the left just because. Oops, I lost a carbon. Like that. So that's the products after one Hofmann degradation. What happens after a second Hofmann degradation? Oh, it's getting real crowded. Alpha beta. You've only got one beta, so it means you're going to make that little baby green product. You've only got one beta, and it's that armpit beta. Means you're going to make that baby green product. You've only got one beta left. That is your green product. And this is your green product. Beta here, beta there. Yeah? So apparently, let's see if we can highlight legibly. 1,5-hexadiene. 1,5-hexadiene That's this one that made 1,5-hexadiene. Okay. 1,4-pentadiene. That's this one that made 1,4-pentadiene. I'm out of light colors. Maybe we can tell. 2-methyl-1,4-pentadiene. 2-methyl-1,4-pentadiene. And what's the lightest color left? 3-methyl-1,4-pentadiene. 3-methyl. Oh, that's that one. That totally got covered up with blue. 3-methyl-1,4-pentadiene. Isn't that great? So, do you remember our ozonolysis problems where sometimes you were given the product of ozonolysis and told what was the reactant? Sometimes you're given the product of a Hofmann degradation and asked what was the reactant. I think I just said that wrong for ozonolysis. Sometimes you're given the product and told what was the reactant for Hofmann degradation, just like we did for ozonolysis. We got this. That's amines. Amines themselves don't do substitutions and eliminations, but quaternary ammonium hydroxides can. Whew, that was a lot. Okay.